Okay, so let's start with this class. So if you need to do a solar PV design, okay, you need to understand the load that needs to be designed. You need to understand okay, so you need to understand the load that needs to be designed. You need to understand the hours those loads are going to be used. So it's important that first of all, you need to conduct a simple energy audit, a basic energy audit. Okay, and what does that entail? What that entails that you need to count the number of equipment that needs to be powered. You need to know all of them as much as possible. In some cases, you could estimate, but it is always good that you know the number of equipment that needs to be powered, the quantity, how many they are, and their ratings. What are their power consumption for every one of those equipment? And then with that information, you can be able to determine the peak demand or the peak power requirements of the system. And with that peak power requirement, you'll be able to size the inverter. It will be a wrong design if you size a system for example, 500, whereas the peak demand, the load at some point could get up to 700. What that means is that you have under-designed that system. So you need to know what the peak load would be so that you'll be able to size the inverter very well. Now, the inverter represents more like your generator. In some cases, inverters are classified in kVA. In some other cases, they are classified in kilowatts. So you need to also understand the difference between kVA and kilowatt. And I believe we handled that in our first session, where we talked about the power factor. So the conversion factor there is the power factor. Okay. So now, with the information on the ratings of the load, you can determine the peak demand. And again, it is also important you understand the hours of usage. The hours of usage for those loads. Now, the hours of usage will enable you to be able to size the battery bank. It could be possible that you size a load that could run for 6 hours, okay? And you could size it for example, you could size it for 3 kilowatt hour, okay? But what if you were wrong and you didn't do your calculation very well, and that load actually requires maybe 4 kilowatt hour? It means that you have under-designed that system as well. Because before it gets to 4, the number of hours that load needs to run, for example, in this case, 6 hours, the battery will have drained and the load will be shut off. So it's important to understand two important things: the power requirements in terms of the peak demand and the energy requirements. These are the two basic things that you need to know: the power requirement and the energy requirement. In our first class, I had explained the difference between these two, and they are not the same. Most times, even we engineers misuse these two terms. They are not the same. So you need to understand them. And doing a simple energy audit will help you to determine what the power requirement and the energy requirement would be. And that's what I have done here so far. If you look at the table, you see the equipment that needs to be powered, look at the quantity, look at their ratings. And then here you have the power demand for the sum of the equipment. So you have 2 televisions, 50 watts each. The 2 of them will give you 100 watts. You have 1 fridge, 150 watts will give you 150 watts. You have 8 light bulbs, 15 watts each will give you 120 watts all together. Then you have 1 standing fan, 40 watts, and you have 40 watts. So when you sum up all of this, their power requirement, you have 410 watts. 410 watts. Then you need to also understand the hours of usage. So for the television, they run it for 6 hours. For the fridge, they run it for 12 hours. For the light bulb, they run it for 8 hours. And for the standing fan, maybe they run it for just 1 hour. So if you now want to calculate the load, the energy requirement, it will be you multiply the power requirements times hours of usage. You get the energy that is required to run that equipment for 6 hours. So that we have done here, and we have established that the total energy storage size that we need is 3,400 watts hour. 3,400 watts hour. The power requirement is kilowatts, is watts, okay? If you're doing kilowatts, you have to divide by 1,000. So let us size the inverter. in this situation now. So our peak load is now 410 watts. 410 watts. So also pay attention, like I said earlier, some inverters are classified in kilowatts, while some are classified in kVA or VA. So you need to pay attention. If it is in VA, you need to apply a power factor to bring it down to watts. Okay. So assuming that the power factor is 19, okay, I think I need to correct this. And then we will need to, if I correct this, I will need to reduce some of this calculation because the power is given in watts. So I don't need power factor anymore. Okay, I used to have this in VA. That's why I have this power factor, but I changed this to watts because most of the inverters that I'm seeing in the market now are now being reflected in wattage. So I decided to also make this presentation to correspond to with the market reality, and that's why I changed it to watts. However, I forgot to remove this power factor. So I'm going to correct this calculation now. I'm going to remove power factor from this calculation. If it was in V, if you have a question, if anyone has a question, please feel free to ask. Right? Yeah. So in the end, this slide.
Please, the power factor. Okay, maybe for this system is 90%, but I think for most system is 80%.
Yes, you can. This is just assumption that it is 90%. You can use 80%. But in reality, have you tried to measure the power factor of your building or of your house? I don't know if you have done that. Now, the reason I'm saying this, we also have to also compare the reality and design. For design purposes, please use 80. For design purposes, please use 80. But 80 is not an ideal power factor. If you go to some other countries, if you go to advanced countries, their standard power factor is higher than 80. Okay, but for design purposes, just to accommodate all allowances, okay, we can use 80. Okay, but in this case, I'm taking away. In this case, I'm taking away the power factor.
Okay, Mr. Chiva,
okay,
most of the housing power factors are very badly done. Sometimes something go lower than that. So were we supposed to determine the one from the building first before we can calculate?
So like I said, for design purposes, please use 80. For design purposes,
75 is what I use.
You can decide to use 75, but however, whatever you're using, state it. Yes, state it. Okay, yes. So if we're not taking away the power factor, we are not dealing with, so we know our peak demand to be 410. So that's the load we want to power, 410. How do we size the inverter? Ideally, we will have just used an inverter of 410 watts. I mean, if you're looking at it from the, so, but if you get an inverter of 410 watts, what you've done is that you have not created room for tolerance. You have not created room for additional load. So based on that, we come in with a concept of load factor. So if you have an inverter that is 410 watts, and you don't want to load it to 100%, because if you load it up to 100%, that is when it becomes, you have used all the capacities of inverter. But what happens if there is a surge? Okay, if there is a surge, what means that inverter will ultimately get damaged. Also, what happens if you now get an additional equipment into your house? What that means, you need to get a higher capacity inverter. So in our design purposes, we have to assume that the inverter is not loaded up to 100%. So that is what we now refer to as load factor. I think I explained this in our first session. So we assume a load factor of 70, meaning that if the inverter can do 100% work, we want to load it to up to 70%. We don't want to load it beyond 70%, so that if there is a surge, it can accommodate that surge. And if there's an additional load, maybe for example, we bought additional equipment into the house, we can also integrate it into the inverter system. Okay, so that's the reason why we have to introduce load factor. So in our design, we are using a load factor of 70. So this peak demand, we divide it by the load factor. If you divide it by the load factor, like I said, some of the calculations are going to change. So let us divide 410 by 0.7. 410 divided by 0.7. Okay, so this will give us, if you have your calculator, or you can also do with your phone, please, let's do this together, right? Let's work together on this.
585.7.
585.7, correct. So this is the inverter side that we require, okay, to be able to carry this load and still have about 30% tolerance. So if you're assuming that you want to get this inverter in VA, that is a volt ampere, what would you do? If you want to convert this into VA, that is volt ampere.
You divide by power factor.
Exactly. So this is the point where I mentioned that if you've gone to the market and you see an inverter that is rated in VA or KVA, and you need to convert it to watts or kilowatt, you use a power factor to do that conversion. Okay, so this is just it for the inverter. It's very simple and straightforward calculation. Now let us do a simple exercise. Can you see my screen?
Yes.
Yes.
Okay. I think I put that from the presentation mode. So look at the exercise there. The exercise number 1. Can you please attempt it and then tell me what your answer is? It's just a simple calculation that just to make sure that we are following. If you don't
1,250 watts.
Okay, 1,250 watts. Did anybody have any challenge doing this? I want to make sure everybody is following. Do anyone have any challenge getting this? Okay, fine, great. So let us look at the battery size. Now we've determined what the size of the inverter would be for our design details. Now, remember that from our table, our battery size is 30,400 watts or 3.8 watt hour, 3,400 watt hour or 3.4 kilowatt hour. They're the same thing. 3,400 watt hour or 3.4 kilowatt hour. They're the same thing. So that is the battery's capacity that we are sizing. Okay, so daily energy need is 3,400 watt hour, okay? But of course, because it's a solar system, we should take into consideration that there could be some days when it rains all throughout. There is no sun that day, okay? And in some part of Nigeria, it could go on for 2 days or even for 3 days. So for those days, we classify them as days of autonomy. So when you're sizing your battery system, you need to take into consideration days of autonomy. These are the days when the sun did not shine, but of course, your solar system still needs to work. Your design still needs to power those equipment. So you take it into consideration when you're sizing your power bank or your battery capacity, okay? So for this our design, we are considering 2 days of backup or autonomy, okay? 2 days. So if there is no sun for 2 days, we want to make sure that we have adequate storage that can sustain the load for that 2 days, okay? So what we can do is we multiply these 2. Okay, these 2 days plus the initial 1 day, that will be 3 days, right? So we multiply this number by 3. Okay, so that is how you get your total battery capacity, okay? So let me just read what I have here. However, 10,200 watt hour is the usable size. So if you multiply 3 by this capacity, remember we have 2 days of autonomy plus the 1 day, okay, that's before the sun did not shine. So that's 3 days. So we're sizing a battery that can accumulate energy for 3 days. And that's why we multiply 3 by 3,400 to get 10,200. That's how we got this 10,200. Now, this 10,200 is the usable size. That's the amount of energy you need to power those loads for 3 days. So for a battery with a 50% depth of discharge, 50% depth of discharge, I think we discussed depth of discharge in our first class, okay? So if you have a battery system, you do not take away all the energy in that battery system, otherwise you will damage the cells. So for every battery technology, there's a manufacturer's recommended depth of discharge. So for most lead acid battery, it would be about 50%. For most lead acid battery, it would be about 50%. So if we assume 50% depth of discharge for this battery in our design, okay, what we will do is to divide this total battery storage capacity by the depth of discharge. So the battery size will now be equal to usable capacity divided by the depth of discharge. If anyone have any question, please.
Please, what is the DOD for deep cycle batteries? We don't use lead acid batteries for inverters now. It's deep cycle.
Okay, thank you very much for that. Like I mentioned, there are different battery technologies. Even in the same battery technology, there are different chemistries. So it is very, very important that you find out the chemistry and the technology you're using and find out the manufacturer's recommended depth of discharge. So for deep cycle battery, they're talking, deep cycle battery are also lead acid, not wet. Yeah, they're also lead acid, not wet. There is AGM, there is this other one, but they're all lead acid. So for those kind of deep cycle, you can go as much as 50%, but you need to make sure you check what the manufacturer has stated, so that you don't damage the cell before the battery reaches its life cycle.
Okay.
Yes. So we have the deep cycle you're talking about is lead acid. We also have the lithium-ion battery. Now, in the lithium-ion battery, you also have different chemistry in the lithium-ion battery. Okay, there's lithium-ion phosphate, which is the main one that lasts longer. There is another one that is, I think it's NCM, nickel, copper, cobalt, manganese. That one has a lower, it's still lithium-ion, but it has a lower number of life cycle compared to lithium-ion phosphates. So it varies. There are different chemistry, there are different technologies in battery. So it is important that you know the technology that you want to recommend, and then browse the internet or check for the manufacturer's recommended depth of discharge. Okay. So thank you for bringing that up. Okay. So if we now divide it by the depth of discharge, we will now get the actual battery size that we will require, which is now 20,400 watt-hour. That is the actual battery size that we require. Meaning that we can, out of this 20,400, we can only take away 50% of it and leave 50% in it. Okay. So now, when you go to the market to buy batteries, you're not going to see the ratings on the battery as watt-hour or kilowatt-hour. In some cases, though, you will find them. In some cases, batteries most modern lithium-ion batteries, okay, that comes in this it comes in a kind of a rack, you know. They will state it in kilowatt-hour. But if you're buying the normal battery that have car configuration or car shape, what you're going to see is 1 amp-hour and voltage. Okay, so if you go to the market and you see a battery that's rated in voltage and amp-hour, how do you calculate the amount of energy that battery contains in terms of kilowatt-hour or watt-hour? That's the calculation I did here, okay? So if you want to know the amount of energy that battery contains in terms of watt-hour, you simply multiply the voltage times the amp-hour that was stated in that battery. Okay, so once you do that, you will now convert, you get watt-hour, which becomes the energy storage capacity of that battery. Okay, so let us take a look at. Okay.
Can we go back to the previous slide?
Okay.
Like,
okay.
what's the value of T in that E equals to into bracket V multiplied by I multiplied by T? Like, what does the T stand for?
Okay. Oh, I didn't even state that in my definition here. So T stands for time.
Okay.
Yeah, this T stands for time. Now, if you look at this equation, let me explain what I have done here. So, of course, we know the equation for power. Power is equal to voltage times current. But voltage times current is apparent power, not real power. And that's why I put this power. It's only when you multiply it by the power factor, it becomes the real power. So ideally, this unit here should be VA. Ideally, if you're doing voltage times current, then this unit should be VA. But because I want to remain in watts, that's why I put power factor here and I put it in Fence column. there has to be power factor for this thing to be in wattage. Okay, and we know that.
Sir, I want to ask a question on the power factor.
Okay, sir.
How do you determine power factor? I'm not a mechanic. I'm not a electrical engineer. I'm mechanical. How do you determine? How do you find power factor of any load or any device?
Okay, you have to use a tool. You have to use a power analyzer to be able to determine the power factor. It's not something you can determine. Yes.
Power what?
So you need to
there's an instrument. There's an instrument for measuring power factor.
Yes, there's an instrument. You can use power quality analyzer to check that. And there are also there are also instruments that you can use to make to determine power factor.
Like okay, what? Power quality analyzer and what?
There is power quality analyzer. There are clamp meters that can also tell you power, the value of power factor. Clamp meters.
Clamp meters?
Yes.
Okay. Okay, no problem. I've got what I want. Thank you, sir.
Okay. Okay. You're welcome. Okay. So now the formula for energy, if you all remember, energy is equals to voltage times current times time. That is energy. Okay. So we can now recall that this current times time is equals to amp hour. That's what I've done here. Current times time is equals to amp hour. Okay, so if you replace this IT here, this current times time, if you replace it in amp hour, you will now have that energy is equal to voltage times amp hour, which is what you see in batteries. When you go to the market for battery, you see the voltage of the battery, you see the amp hour of the battery. If you multiply both of them, you get the energy that the battery can hold. That is the calculation I have done here. And T stands for time, please. Okay, so let's take an example. So the example is calculate the number of batteries required to produce 4 kilowatt hour. 4 kilowatt hour of daily energy need plus 3 days of autonomy. I think I changed this to 2 days, sorry. So plus 2 days of autonomy for non-sunny days using lead acid batteries with the following rating. So the battery is rated 12 volts and it's rated 200 amp hour. And the depth of discharge, recommended depth of discharge is 50%. Okay. So that I need to make a little correction here. You know, the energy that we're calculating is 3,400. 3,400. So I need to change that here. With this example here. So it should be 3.4. Okay. So the example states calculate the number of batteries required to produce 3.4 kilowatt hour. Okay. So daily energy need is 3.4, not 3.2. It's 3.4 kilowatts hour. That's the daily energy need. Okay. But we also require 2 days of autonomy in case there is no sun. 2 days of autonomy. So we multiply 3.4 by 3. So for 2 days of autonomy, we have 3.4 times 3. That will give us 10.2. I need to confirm that. 3.4 times 3. Okay, so that will give us 10.2. So that's the energy storage size that we need for the battery. Okay, so now the actual battery size at 50% DOD, it is the total energy storage size that we need divided by the depth of discharge. So if we divide it, we'll have 20.4 kilowatt hour. So this is the battery size that we want to design. And this battery size should be able to carry on the load for 3 days. If there is no sunlight for 2 days, it should be able to sustain the load. Okay. So this is the total battery size that we want to have. Now, if we go to the market to buy these batteries, you will see that the battery is rated in 12 volts and 200 amp hour. 12 volts, 200 amp hour at 50% DOD. Let us calculate the specific energy of one battery. Okay. One of the batteries. So the specific energy storage of one of the battery is 12 times 200. 12 times 200. That will give us 2,400 watts hour or 2.4 kilowatts hour. Okay, so the total number of batteries required is 20,400 watt hour or 20.4 kilowatt hour. Please don't get confused when I use watt hour and kilowatt hour. They mean the same thing, only that for kilowatt hour I have divided by 1,000. Okay, so we're designing for 20.4 kilowatt hour divided by 2.4 kilowatt hour for one of the batteries. If you do that division, you will have 8.5 number of batteries. 8.5 number of batteries. Of course, you cannot buy
2.4 kilowatt hour, not watt hour.
Thank you very much.
Yeah.
Yeah, thank you very much. Yes, 2.4 kilowatt hour. Okay. So if you do that division, you can have 8.5 number of batteries. But you cannot buy half battery in the market. So you approximate it to 9 number of batteries. But again, you need to be careful in determining the number of batteries that you need to buy, because one thing that determines the number of batteries you need to buy is your system voltage, the voltage of the system you're designing. So for example, if you have an inverter that uses 24 volts, an inverter that uses 24 volts, and then you have a battery that has 12 volts, what do? It means that you need to combine two of these batteries to have 24 volts, right?
Series.
You have to connect it in series to have 24 volts, right? So if you're connecting it in series, it means that you need to, so you cannot use 9 batteries. If you're using 2 to get 24 volts, you cannot use 9 batteries for this design. Assuming your system is 24 volts, you cannot use 9 batteries. You can use 10 batteries or 8 batteries.
You said you can use what, sir?
You can either use 10 or you go down to 8. You
It must be
use 9.
even.
Yes, it must be an even number. Okay, so assuming that the system we are designing is for 24 volt system, then we cannot use 9 batteries. This becomes 10, or we go down to 8. I don't know if you understand that.
Yes.
Okay, great. So now we know the number of batteries that we need. We need 10 batteries to store this amount of energy, to store 20.4 kilowatt hour of energy. We need these 10 batteries to do that. So we now know the number of batteries we need. We have determined the size of the inverter. Now we have also determined the size of the battery that we need. Okay.
Can you increase your screen, sort of? I don't know.
Okay, it's because I'm making some changes. Okay, let me go back to presentation mode. When I need to make changes, I'll come back to this.
Okay, thank you.
All right, thank you. Sorry. So this is where we are. And I said that the approximate number of batteries we need is 10 batteries, assuming the system is a 24 volt system. But if it is a 12 volt system, you can still do 9 batteries. If it is a 12 volt system, you can still use 9 batteries. If it's a 12 volt system and your battery is 12 volts, you can use any number of battery that you like. Okay, so that is another determinant. That's something that determines the number of battery that you use for your system.
Sorry,
okay.
I want to ask something about the connection. Now,
okay.
If we're using a 24 volt inverter, and then we have a 10 series of battery, like 10 numbers of battery, does that mean our first 2 batteries will be connected in series to give us 24 volts, and the rest will be connected in parallel? I just want to clarify.
Thank you very much. Every 2 of the batteries will be connected in series. Every 2, you have 10 batteries, right? So you connect 2 in series and you have 5 in parallel.
Okay.
Is that clear? So you connect every 2 of them in series to get 24 volts, and for the you connect them in parallel. Exactly. Thank you.
No, I think you are wrong, Bo. Because you can't do that. The batteries is rated 12 volts. When you connect 12 volts in parallel with 24 volts, the equivalent voltage is not going to be 24.
So when you connect two batteries in series, you have to.
Yeah, that's 24. But when you now connect another 12 volts again, in parallel with that series connection of two batteries, you will not get a equivalent voltage of 12 volts again.
When you connect the two batteries in parallel, the voltage remains the same.
It remains the same, yes. That's when all the voltages are the same.
The amperage, yeah. So you have 10 batteries, right? So 2 of them, every 2 you connect in series. So you have 24. So you have 5 series connection, correct?
Okay, fine. Now, then the batteries are no longer going to be 10. They are going to be 20.
No.
If you want to achieve.
No, sir.
You have 10 batteries are connected in series. 2 of them form 24 volts. Then each of the among the 5 pairs, each pair is 24. Then times 5. When the 5 pairs are connected in parallel, it forms 24 volts as a parallel connection. I don't know whether I'm right.
Yeah, you are right. Then okay, still 10 batteries, but in 5 pairs.
Yes.
Yeah, in 5
pairs.
That's correct.
Okay, so thank you. If there's any confusion, if there's any, please speak up. Let us clarify. Okay, please. I cannot assume that you understand everything I'm saying, but if you speak up, then I can clarify further. Okay, we have people who have also have experience in this that can also, contribute. And that's
my confusion is, how do you do the physical connection in parallel, not in series? I know in series is connecting positive to negative. Then how do you do the physical connection in parallel?
Okay,
it's negative to negative, positive to positive.
Okay. Hello, the ampage, while you are talking about the voltage, you are not measuring the ampage, because the amperes might likely change whether in series and in parallel. So when the voltage in series, the voltage will remain the same when you connect it adds up when you connect in series, the ampage remains the same. But in parallel, when you connect in parallel, the voltage changes and the ampage remains the same. I want us to clarify that as well.
No, my question is this: is not about changes, is the physical connection. Like I know when you are connected to batteries in series, you connect positive to negative. I know it's series connection. Now, assuming these are case study, we have 5 pairs of batteries. How do you connect them in parallel?
Negative to negative.
Okay.
Did you get it? Yeah, so it's correct. You connect negative to negative. Positive
Just like when we're doing boosting, trying to get a power boost for a car that has stopped. We connect in parallel.
Okay, thank you, sir.
Yeah. So thank you very much for that. Thank you very much. And like one of the participants said, if you connect in series, you are increasing the voltage. Okay, in series. But if you connect in parallel, the voltage remains the same. However,
current increases.
The current increases. Yeah. Okay, so that's what one of the colleagues has.
Yes, that's what I'm trying to exactly. Thank you, Chima, for that.
Yeah. Thank you very much. Yeah, you're very much correct. Okay. So here is just example and exercise for us to try on. Okay, so this is saying that calculate the number of batteries required, assuming 1 day of autonomy. Remember, in our example, we used 2 days of autonomy, but assuming 1 day of autonomy is required using a lithium-ion battery with a depth of discharge of 80%. Now the battery is 12 volts and the amp hour is 100. Now using this same example that we did, and then use the same example that we have on the screen, use it to calculate for this exercise. And let us see what we have.
So the only difference is that we are using 1 day of autonomy.
We're using 1 day of autonomy. No, we're using 1 day of autonomy. The depth of discharge is 80, and your battery capacity is 12 volts, 100 amp hour, not 200.
Okay, 100 amp hour, and then day of autonomy is.
The answer is 7 batteries. Okay, so, it's 100 amp hour. Okay, sorry. I thought it's 200.
No, it's 100 amp hour battery.
It's still 7 I got. 7 batteries.
Mhm. Did anyone get something different? Did anyone get something different? If you have something different, it means that you've done the wrong thing. I need to be sure that we all get these calculations correct. Seven, correct. So if you're not getting 7, then you've done the wrong thing, please. If you're not getting 7, you've done the wrong thing. So let us go ahead. So now we have sized the battery, we have sized the PV system. Now let us size the we have sized the inverter, we have sized the battery. Let us size the PV system. Now remember, we started from the energy, we now went to the inverter, the battery. We are now coming to the PV system, because the PV system is, you cannot start on the PV system and then go downward. It's the other way around, from the load to the energy, to the inverter, to the battery, and you now come back to be able to size the PV system so that it can provide such amount of energy and power for those systems. So using the sample load details that we have previously, let us now calculate the size of PV that is required. So required PV energy output, the energy that we want that PV to produce is 20,400 watt-hour. That's the energy we require that PV to produce. Okay. Now there's something we call peak sun hours. Peak sun hours. I explained this in our first class.
Excuse me, sir. I have a little confusion on the sizing of the inverter. It's unfortunate I didn't start on time with the class. I'm sorry. For a little bit during the class backward. I'm sorry. Please, could you just give me some hint about sizing the inverter itself?
That would mean going back to the first slide. It's a simple calculation.
I'm sorry, sir. I'm sorry.
Why can't we do that after the class now? Are we going to be going backwards like that?
Now, so we can always go back.
Let's finish the PSA first, and after we come back.
I think we should go with we should just go ahead, and then I'll come back to that, sir.
We come back, because otherwise we lose our own trend as well.
Please, let us also be considerate of other people's time here. I'll come back to you, sir, on the inverter, and it's a very simple calculation, but I'll come back to you on that.
There's no problem, sir. Thank you.
Okay, let me finish this one. I will come back to you. Now, usually, please mute yourself. Mute yourself. You cannot speak. Mute yourself, except you have a question to ask. So using the same simple sample load that we had before, which has given us that the load that we need is 20,400 watt-hour. That the solar PV must be able to produce this amount of load. And there is something we call peak sun hours. So peak sun hours is not the same time as when the sun comes out till when the sun goes down in the evening. It is not the same time. Okay. Peak sun hours, I explained this in our first class. It is assumed that the sun comes out in the morning and it is hitting 1,000 watt-hour per meter square, 1,000 watt-hour per meter square. Okay, if it is sitting 1,000 watt-hour per meter square, how long will that sun stay? Okay, so I don't want to go back to the first class, but I want to assume that most of us here attended the first class. Okay, and that is the importance of attending the session from beginning, so that you don't you can follow up as you progress. I know I've explained what is peak sun hour. I don't want to go back to explaining what it is. But peak sun hour, we are assuming that the peak sun hour is 5. That's the assumption. Peak sun hour is 5.
For Nigerian climate is 6 now.
Now, if you go down to the south, in Nigeria, it cannot be 6 because you have less sunshine in the south. But if you come towards the north, toward the northern part of Nigeria, yes, you can use 6. But for design purposes, for Nigeria, please use 5. For design purposes, in Nigeria, use 5.
Okay.
So that you don't overestimate. Okay. So that's an assumption that for peak sun hour, we're using 5 in this case. Okay. So if you want to now determine the size of your PV, please divide the total energy that you want that PV system to produce. The total energy, including those days of autonomy, right? Calculate them. Okay, so the total energy we need is 20,400 divided by the peak sun hour, which is 5. Okay, so if you divide it, you will arrive at 4,080 watts. 4,080 watts of PV system. So you need a PV system of 4,080 watts. right? But the challenge is that 4,080 watt, it's at standard test condition. At standard test condition. So it is at laboratory test condition. That's when you will have 4,080 watts. And the standard test condition we mentioned in our class is 25 degrees centigrade.
Excuse me, please. Excuse me.
Okay, go ahead.
The required energy output of 20,400 watt-hour. Have you taken into consideration the autonomous days that you mentioned?
Yes. It has been taken.
The backup. It has been factored in.
Yeah. It has been factored into the
everything is there.
Yeah. It has been factored into that. Yes.
It's okay. Thank you.
Just quickly, let me confirm. What? Okay. You will find out that our total energy here is 3,400. So we are factored in that days of autonomy, right? So the PV need to produce 20,400 watts hour, and we have divided by the peak sun hours to have 4,080 watts. Like I said, it's at standard test condition. Assume that the sun comes out and it's hitting 1,000 watts per meter square at 25 degrees centigrade. Now, those are the standard test conditions. So, but we need to get the actual PV size. Now, getting the actual PV size, we have to divide that theoretical size that we have as standard test condition by the performance ratio. There's what we call performance ratio. Okay. Now, the performance ratio is assuming your PV is rated 400 watts. Okay. So if there's a 400 watt is a standard test condition, but because you're not operating a standard test condition, the losses will reduce the output from that PV system. And that losses is what we now know as performance ratio. Okay, so performance ratio is the theoretical design of the PV system divided by the actual output of the PV system. That will give you performance ratio in formula times. So performance ratio, we have to divide the theoretical PV size by the performance ratio. So if you assume a performance ratio of 75%, meaning that if you have a 400 watt PV system, you only have 75% of its output. Okay, that's the assumption here. So this performance ratio will now enable us to be able to determine the actual size of our PV. So we divide it by 0.75 and we'll now have 5,440 watts. 5,440 watts. Okay, I'm tempted to begin to explain all of these times again, performance ratio, peak sun hour, but I know we've dealt all of them in our first class. So I don't want to go back to start explaining what they mean. Okay, so you divide by your performance ratio and you have 5,440 watts. So this is the size of the PV system that you need to be able to produce the energy that you need. Okay, and this PV system, it's assumed that this PV system will function for 5 peak sun hours. So if this PV system functions for 5 peak sun hours, you produce this amount of energy. That is the idea of the design. So are we clear on this? Are we clear on how we're able to establish the size of the PV system?
Yes.
Yes. Okay. If
what of the modules? The number of modules.
So if you want to, the number of modules now determine on the size, on the capacity of each module. So if you go to the market and you find 400 watt peak, how many number of modules would you need?
That's 5,440 divided by 400.
That's 20 something. 21.
21.
5,440 divided by 400.
Yes. Please do the calculation again.
That is 12.5, around 13.
14 pieces.
Exactly.
Please repeat your question a little more. Please repeat your question again, please. Don't be offended.
14 pieces.
It's 14.
The question is, if you go to the market and you see a PV module that is rated 400 watts, 400 watts. How many number of that panel would you need to generate 5,440 watts?
It's just to divide it now, that's all.
Exactly. So
It's
that's what we do.
13.
13.6, approximately 14, correct?
14, yes, 14.
Exactly. So we have 14 numbers of PV module.
But I don't think we have 400 in the market. I think it's 350 we have.
We have 400. We have 400. We have 400. So in fact, we have higher than 400 now.
In which market now?
We have about 560 from Jinko. Yes.
Okay. What we see is mainly 350.
Yeah. And be careful as well. Sometimes when you're going out to buy this equipment, please, as an expert, let us be careful. Sometimes buy from authorized dealers. Sometimes somebody will take up a PV module of 300 and change the level to 400. So if you're doing an installation, please test and be sure of the capacity that you're buying. Because this is one of the
tests, sir.
Sorry?
How do you test? So how do you test the capacity of the module you are buying? How do you test it technically?
You may need to test the voltage and the current that it is producing.
Okay.
At certain point. So you can go with your multimeter. Yeah, multimeter, exactly. You take the voltage and the current that it is producing, and you compare with the rating that is given on the PV panel.
Okay.
Yeah.
If you're in Lagos, you can come to Pan Atlantic University. We'll test it for you, free.
Hello, sorry if I may ask.
You say it can go to where?
Are we going to have any difference buying the polycrystalline or monocrystalline module?
What?
Is there any difference in polycrystalline and monocrystalline module?
Or hybrid?
Is the efficiency?
Yes, of course, the efficiency varies. I discussed this in our first class. I discussed about the monocrystalline, the polycrystalline, and there's another one, thin film. We discussed this in our first class. There are differences. The efficiency varies.
So which one is the most recommended?
Mono is better. Yes.
Okay, thank you.
You're welcome. So
sorry, please, before I mute myself, I would appreciate if you could recommend brands of batteries, solar panels, and inverters. I'm not saying you should market anyone here, but at least maybe give us like the three most recommended brands of respective products. So that I would appreciate if you could give us recommended reliable products that can be specified for anybody preparing a bill or
battery, inverters, and modules.
Yes. Thank you.
Maybe we could have that towards the end. We could have that towards later, so that
I could make some recommendations. Okay, and I'm even trying to see if I could bring one of the OEMs, one of the agents of the OEM to speak to us on that. If that happens, that will also add to the valuable. We are seeing that discussion.
Okay. Hello, sir.
Then, sir, about the inverter stuff, could you please just, even if it's a minute, I'm pleading to all.
Hello.
Okay, hello. Yes.
About the inverter sizing, please, sir.
But please, if you are talking of inverter sizing, it's as if you are taking everybody back. So I think you can create time to do something about it, so that we'll go forward.
Yes, I'm almost coming to the end of this.
It's almost done. It's almost done. It's about 3 sizing that are required. I think the next thing is just controllers. So if you can take him back and then bring him up to its speed, and that's okay.
Thank you, sir.
Then I want to ask a question, sir. Okay. With respect to the performance ratio, that's 0.75.
Okay.
Now, is there any reference for it, sir? Because there are some things that they will ask you to get a reference, as in where does that 0.75 come from, if we are to reference that?
So performance ratio varies across board. Okay. Now, in the first class, I explained how performance ratio is being affected. Now, performance ratio is being affected. If you deviate from the standard test condition, the performance ratio begins to change. So it depends on the level of deviation from the standard test condition. So for example, if you do an installation and the PV module is rated 400 watts, and the temperature of that PV module is 25 degrees centigrade, and the sunlight hitting that PV module is 1000 watts per meter square, you will get, and there's another third condition, which is the air mass of 1.5. If these three conditions are met at these numbers, you will have 400 watts. If that PV is rated 400 watts and you put them in these three conditions, their PV is expected to produce 400 watts. But we all know that the system changes. If you're installing the PV system in the north, you have higher solar radiation in the north. But again, you also have higher temperature there. So the higher temperature will now increase the temperature beyond 25 degrees centigrade. You might even have up to 45. So for every degree centigrade that you go higher than 25, you have what we call the ratio of voltage drop. The voltage begins to drop. And when the voltage begins to drop, the power output also drops. And that is what affects the power ratio, the performance ratio, right?
But
so,
there are graphs. There are graphs who can read this off. You know, he was asking for a reference. Can't we use those graphs to pick up the PR? As temperature increases, it decreases. So there are several graphs that we can use, charts we can use to get rid of that. Can we do that?
I think what Engineer Uche should tell us is that this 75% is conventional, and then we'll take it as a conventional value.
No, we need to know exactly for a particular location. If I'm Maiduguri, you need to read off exactly what is the PR.
But the PR is dependent upon the temperature of the module.
That's what I'm saying. There is graphs which has been done, which you can read it from. You can read out those PR for various temperatures. There are, you know.
If you use the software to select your location, I think the software will equally suggest you some of the performance.
Yeah, gentlemen. So it is there are standards. So if you purchase a PV module, they will tell you the temperature coefficients. The temperature coefficient, you can now use that if you want to determine this by yourself. You can now measure what the temperature at this location where you have installed that PV. What is the temperature at that point? Now, mind you that performance ratio, it is not constant. So during rainy season, you could have a lower temperature. During dry season, you could have a higher temperature. So performance ratio is based on the actual output of that PV system over a period, the average over a period of time, maybe 1 year. Okay, so if you do a little research for the location where you.
Hello, sir.
Hello.
Hello, sir.
Yes, I'm
I have a question. Does aging affect the performance ratio of a PV system?
Of course, yes.
Then, you know, all this while we'll be talking about the natural stuff, the physical environment, temperature, etc., etc. Then, how does aging affect the performance ratio of PV system?
So when you buy, some of these details you're asking are provided in the PV model or from the original equipment, that is the manufacturer. Now, for some of the PV system, for every year, they have like a 0.5% degradation. So their performance dropped by 0.5. Some of them can be 1%. So every year, the performance of that PV drops by a certain percentage. It is the equipment manufacturer will always provide this information. It is not the same thing for every PV models. And this is also how you these are the things you also look at when you're buying PV model for projects. You look at the one that has the least degradation over the period. So for a PV system that has up to 25 years lifespan, it does not mean that after 25 years, it will no longer produce electricity. It will still produce electricity, but the degradation will have maybe gone down to about 80 or 70%. The same thing happens with your battery. Every time you charge your battery and discharge it, it counts for one cycle. And batteries have a number of cycles.
Yeah, they write it there. It's
Yeah, they
written
always
there.
write. They always write it. For lithium ion phosphate, it's about 6,000. Okay, so this is these are the information you also need to look out for when you're choosing your product or your brand. Okay. So for every year, the solar PV drops, it degrades. Okay. By standard, I would say it's 0.5%. By standard, anyone that does more than 0.5% might not be the top quality in the market. So, but the technical documents of the PV model will give you all of these details.
It's very clear. We should check up on the manufacturer.
Sorry, when you say 0.5%, that represents 50%. Does it mean 50% drop in performance on a yearly basis?
No, 0.5% is not
0.5%. 0.5%.
That's what's
okay. No, 0.5%,
not 0.5. 0.5%.
or
That is
0.5%.
Yeah, that's 0.005.
Okay, 0.005. Yeah. Okay.
Exactly. Yeah. Okay. So now we've been able to size we've done the inverter, we've done the battery, we've done the PV array. There's one thing that is remaining, which is okay. Let's also do an example. Let's do this exercise. This number 3 exercise. So calculate the actual PV size if performance peak sun hour is 4 and performance ratio is 65%. What will now be this PV size that is required here?
$7,846.
Okay. Did anyone have something different?
7,840.
Okay. Did anyone have something different? If you got something different, please speak up. Let us help you. You may have done something different. So you have 7,846 watts, and if you have 400 watts PV system, you divide it by 400 watts, and you get the number of PV modules you need to buy. So let us move ahead to the charge controllers. Now, using the same sample load details and data from the previous example, okay? Now, the previous data we have is 20,400, and we have a battery voltage of 12 volts, and we have a solar array of 5,440. I need to change this.
Sorry, let me quickly just ask a question. For the PSH, how do you establish PSH? Are there established figures already? Say, for example, in Nigeria, across different areas in Nigeria, are there established PSH across Nigeria, or there's a chart that shows different PSH?
Nigeria 5.
Oh, the average in Nigeria is 5.
Yeah, please, for design purposes, please use 5. If you're doing somewhere in the southern part of Nigeria, it is
in Sokoto we use 6.
Yes, in Sokoto you can use 6.
Please, Mr. Chima, can we just go back to that where we say let's use a fund peak sun hour
That's
for 4.
in the south. In the north is.
Hello, can we go back to the last slide? That question.
Okay. Oh my goodness.
The exercise.
Hello.
No, I'm coming. What have I done? Just a moment, please.
That one.
Okay, this is the point. This is the slide.
The question.
As you said, it's 7,000 watts.
7,846.
Is it not 2,400 divided by 4 and then divide further by 0.65?
Yes.
Yes.
It's my calculator is easily 40. Is it not?
Yes.
That's the answer. 7,846.
846.
Yes.
Did you get something different? It is.
I was getting 12,000 something. I was wondering why.
No.
Maybe it's my calculation. Is it not 20,000 divided by 400? 20,000 divided by 4.
20,400 divided by 4.
Yes, and then
divided by 0.6,
divided by 0.65.
Divided by 0.65, isn't it?
Yes. Do it well. It's 7,846.
Please let us know. Did you get that now?
Yeah, 7,846. Yes.
Okay. Yeah, please.
We need 20 rows arrays, because if it's 400 watts rated,
20 modules.
Yes.
20 modules too.
So
An array of
if it is important that everyone tries this calculation, because there could be something that you're getting wrong or you're missing. So that's why I included all of this exercise, just to to walk us through the process and be sure that we all follow, please.
20 years.
Yeah,
okay,
20.
So let's proceed, please. Everyone, mute your mic. Let us proceed. So using the same sample detail load from the previous example, and we have 20,400 watt hour. We have 12 volts battery system. I will have solar PV array of 5,440. We now need to determine what charge controller we're going to use. Now, the reason why we need charge controller is this. Your PV system produces power. Okay, power is a combination of voltage and current, and it is not stable. It's depending on the intensity of the sun. Okay, but your battery needs to be charged at a constant voltage. So you need something that will keep the voltage constant. If the power increases, it converts the excess voltage to current, keeping the voltage constant. If the power drops, it converts, it stabilizes the voltage and reduces the current. So you notice that when you're charging your batteries through charge controllers, the voltage is constant, but the current will keep changing depending on the increase or decrease of the solar intensity. That is what charge controller does. Otherwise, if you remove charge controller, you will damage the battery. You could be sending different voltage levels to the battery, and it's going to damage that battery. That's why you need charge controllers. Okay, so how do you now determine the size of the charge controllers that you need for this battery system? That's what we're trying to do here. Now, because you need to keep the voltage constant, all you need to do in determining your charge controller's voltage is to divide your total PV array by the voltage of the battery. I need to change this value again. This is 5,440. Okay. So you divide the total PV system by the voltage of the battery. If the voltage of your system, now, please, I need to clarify something here. You're dividing by the voltage of the system, not necessarily the battery. So if you have a 24-volt system and you have a 12-volt battery, 24-volt system, but your battery is 12 volts, it means that you combine two 12-volt batteries to get 24 volts, right? So yes. what you're dividing here is voltage of the system, not battery. Let me also make that correction here. So you're dividing by the system voltage. So when you divide by the system voltage, you have the battery, you have the required charge controller size. And charge controllers are rated in amp. Let me correct this as well, right?
So when you say system voltage, what do you mean? If using more than one battery, for example, is it the combined battery voltage? Or...
Yes, the combined battery voltage, please.
Don't forget to change the battery voltage here to...
Hello. The system voltage should be the inverter voltage.
That's the inverter voltage. Actually,
that's the inverter voltage, exactly.
Yeah. Yes.
Ah.
So because of the idea about the inverter, please, I'm pleading with the class. Please.
He will go back. Let's finish now. He will go
That's
back.
correct.
Please, I have a question. Now that we got 340 votes for the charge controller, any tolerance? If you get to the market, you will not get exactly 340 amps. Are you going to go a bit higher to give some tolerance, please?
It's 454.
No, it's 340 you got just now.
No, that's with the that's correct. It's corrected it now.
Okay.
Just check, he has corrected it.
Okay, if it's 454, when you get to the market now, what rating of charge controller are we to take? Higher one to give some tolerance or what? Higher value.
Chima has gone.
Engineer Uche, please, we need your attention.
Ayodeji, Olule, you are there.
Engineer Uche is also not available.
I think, friends, charger controllers, the current is given in ranges. So when you're buying, you look for the range. You look for the range that matches what you want.
Okay, thank you.
It will not give you a specific value, 40 amps, 50 amps. It will say from 20 to 60, this to this, just like the one you use for motor controls. Yes.
Thank you very much.
You're welcome.
Okay. Hello, can I contribute, please?
Yes.
Hello? Okay. I think with the charge controller, we still need to consider the tolerance. So some people, so their own is 1.25. Now we need to get 1.25 tolerance. That's multiplying the total current we get by 1.25.
So that's 25% tolerance.
Yes, 25% tolerance. Because of
Thank you.
Okay.
Our hosts have gone elsewhere.
They're going to break.
Okay, I've added it. Sorry, gentlemen, I've added him back. I think he left. Maybe in his network.
Somebody was protesting and let off annoyance that his question was not answered about the inverter. So I don't know. I think Engineer Uche,
sir,
we have these notes. People should go back after the class and read their notes.
Because you have only
the next class, they are up to speed.
Okay, see what happened is I'll tell Njachima after this session, Njachima will run through. Oh, we have a lot. I keep saying this. This training is for 2 hours, and it's to not inconvenient us because all of us are busy people. So within these 2 hours, we hit the nail on the head. But notwithstanding, I'll give introduction from Njachima. After now, he will run through the 4 parameters of design again. He will run through the design of the 4 parameters again, right? Then we will now go into the Excel thing. Then next week, when I start next week, I'll run through this thing we have done again for the first 30 minutes before we now go into the software because it's good for people to catch up with what we've done. So the person that protested and left, please, there's no problem because I don't think he has paid. Just don't worry yourself.
And please,
right?
People should know that we are at different points. Some people don't understand this. We have done this solar before. Some people are just new to it. They don't understand it. So you don't expect using you are so grounded on it to intimidate other people, please.
But at the same time, we will not allow those who are still at the primary stage to draw those rapid back. So
that's why I said they should go back to their notes and read it up.
I think this thing is not hard. Since there's a video of previous classes, people should go through the video before coming to class. So it won't
Chima, are you around?
It won't be joining us back.
Oh, he's back. He's back.
That's exactly.
So let's hand over to the coordinator again.
Uche, just hold on. Let me open up the slide. Just a moment.
Okay.
Yeah.
So while Jinachima, we're waiting for Jinachima, please. This training would have been 6 weekends, but you see, the shorter. These are like a crash course. So I will need the understanding of everybody. When I send these videos, go through them. If you have any spare 1 hour, just go through them. You catch up. To bring you up to speed. So immediately with this class, of course, I'm going to send the video maybe today or tomorrow. Find out 2 hours or 1 hour and go through it. There's a whole lot that's loaded in these videos. Don't take any of this training for granted. And it's a 10 hours training spread over 5 weekends. And there's no better arrangement I can talk of.
Please hand over the control to me so I can share my screen.
Okay.
Yeah. Okay.
You can share your screen now, please.
Okay. Is it visible now?
Yes, it's visible now.
Okay.
Yes, it's visible.
Okay. Sorry for the interruption there. Hello, am I still visible?
Yes, you are still visible.
Yes.
Okay. We are almost ending this before the interruption happened. So sorry.
It's thanking us.
Okay, please mute yourself if you're not speaking. Kindly mute yourself. So the design that we had, we've done for we've sized every system components. We've sized for the solar PV inverter. We've sized for the charge controller. We've charged for the batteries and all of that. So with all of that sizing, you can now have a complete system to deploy. Okay. So in summary, we have now. Please, this figure here. Remember, I had changed this.
It's 454.
Yes. Now this is PDF document. I can't change on this very document.
Okay, it's okay.
What we've done so far is that we've determined the size of the charge controller that is needed. This is for something, not this very value that you're seeing here. And we've sized the solar PV that is required. I will size the battery bank that is required. That's all you need to do for an off-grid PV system. If you're sized for an off-grid PV system, this is all you need to do your system deployment. So on this, let me go back to the inverter. Let me just throw a little bit light on this based on the request from
the man has left now. He has gone.
Oh, really?
Yes.
Sir, please continue. I'm around. I've not left. I'm around.
Okay. Sorry.
So he's still very much around. Okay. So for the inverter system, now this is the PDF document that you have circulated before I made some modification. And those modifications, I will effect them. If you're not already doing them on your own, I will effect them. I will recirculate the modified document. Now, the reason is this. The reason why I have some of those modifications is, remember I've told you that the calculations I did in the past, I had used VA, that's voltage ampere, and I felt the need to change it to watts or kilowatt because of the current trend in the market. And I think I didn't delete some of the factors that I needed to be deleted. So this power factor shouldn't be here. Okay, yeah. So for the inverter sizing, it's a simple calculation. The person that is asking this question, you are not here when I talked about the simple load audit. Okay, so I said that before you could do any system design, you must first of all conduct a load audit. You need to know the equipment you're powering. You need to know how long those equipment are going to be powered. If you have that information, what it tells you the peak, the power demand. It tells you the power demand of the system. Okay, and the power demand of the system is what you should be sizing your inverter to be able to carry. Okay, so for this system that we have here, for this table, the power demand is 410. But we cannot put 410. We need to put tolerance. So we divide this 410 by the load factor, not power factor. Please, this power factor should be deleted. I have deleted it in my previous in the PowerPoint that I was sharing initially. Okay, so it should be deleted. So it is load factor. You only divide it by the load factor. And once you divide it by the load factor, you get something. Let me do that division. 410 divided by. So when you do that division, you have 585.7. And that's the size of the inverter that you need. 585. Okay. The person that asked the question, are you clear on this, or are there specific areas you want me to address?
On that, how do you determine the load factor, please, sir?
Okay, so the load factor, the total demand you need is 410. Okay, now 410 is assuming that you have 100% load. 100% load, but you know, if you have that 100% load, sometimes there could be surge that will need your load to go above 410, and sometimes you might buy additional equipment into the house. Okay, so you want to create a gap, you want to create allowance for surge and for additional load that you may buy in the future. So you, instead of loading it to 410, you look for inverter's capacity that is higher than 410, but you want to load that inverter capacity at 70% load factor. So to determine the size of that inverter, you divide this your actual inverter size by the load factor. So you can decide to do 60%, you can decide to do 70%, or you can even decide to do 80%. It has to be at your own discretion as a designer.
Okay, a sort of tolerance, creating for excessive load in future.
Yes, that's what it is.
Okay, clear, sir. You can go to the next stage. I'm clear.
Okay, so you're clear. Okay, so gentlemen, this is the manual calculation of all of this. Okay. Now I developed an Excel. Let me see if I could share that.
Please, can I ask a question before you?
Okay. Please ask your question before I move on. I move on.
Okay. Actually, I'm an electrical engineer, so I am well at home with your calculation. Okay. I'm not in the industry. I'm in the academia. I'm studying, so I may need some of this, as a reference. And I'm in an area whereby if you say V is equal to IR, you have to bracket Ohm's law in front. So please, can I really get reference for all this so that if I have cause to refer to any of them, I wouldn't be queried.
So if you need to refer to any of them, you need to look for people who have done research in this regard. So for example, if you're looking at the peak sun hours, if you're doing a project somewhere around the southern part of Nigeria, okay, you will need to look for people who has done research in that regard, and then look at the peak sun hour that they've established, made based on experiment or based on actual observations. They will have established, okay, this is the recommended peak sun hour. So you might need to reference a research document, okay, or a publication or a global publication. Now, the unfortunate thing is that there is not so much global publication on the Nigerian situation, okay. If you're doing this kind of project in places like maybe US or Germany, you might be able to easily get references in any location. And this is what, if you're using a software like the PVCs, some of these PVCs has also taken some of these assumptions into considerations. They may not be references for them, but they will just, assume that for this location, this is what the peak sun hours, is or looks like. Some of them as well, you could also get them, some of them from NESA data. I think here.
Yes.
You could get some of this data from NESA, like geographical or what do you call it? Some of this data.
Yes.
Yeah, you can get them from NESA, right? And that is essentially what some of this software does. They they plug into the NESA data to extrapolate some of these things. Okay, so it's a very vital question that you have, because you also need to understand how some of these softwares work, because software is garbage in, garbage out, right? Yes. Yeah, so you also need to understand some of how they extract some of these variables in their calculation, because it could they could do the wrong calculation for you if you're not careful. Now the point is some of these softwares, because a lot of people are using them, so they aggregate the data. Okay, they do what we call regressional analysis. So they look at the data of the people who have been using these softwares, and they kind of extrapolate between the available data online to give you a certain value.
Oh, okay.
You understand? So if, for example, a lot of people have been using that software in the Niger Delta, and many of them has been using maybe, for example, performance ratio of 4 or 5. The software will now look at that and then pick that same value and then use it in your own calculation.
Excuse me, please. To help the man further, there was a material you sent to us even before we started the course. This it took us through all the rudiments about power, voltage, and all that. If you can go back to that, you will be able to relate better with what is happening now based on that material you get, even before we started.
Yes.
No, I know those ones, and that's why I started as I'm an electrical engineer. So I actually understand the basics, but my concern was just referencing.
Yeah. As an academician, sometimes you also need to reference some of these things. I understand there are geographical data that you can get. Now the point is that you are looking for a finished information, quote and unquote, right? Whereas you could also get the raw information, like get the geographical data and they establish the information you want to establish.
Oh, okay.
Okay, if you want some more research on PSH, where I can get you somebody who is doing a lot of work on that, and you can get a published data for Nigeria, particularly the south and a bit of north.
Okay. I'll be very happy because I'm not even in Nigeria. I'm in the UK,
okay,
and I'm studying. Nigeria is my case study, so
okay.
I'll be very, very happy.
I will send the address to the organizer. It's in Covenant University, actually. And then you can relate with them. There are you see things they've published and so on. I think that's a very good reference.
All right, thank you, sir.
Thank you.
Okay. Thank you very much. I really appreciate the collaboration that is going on in the house. Like I said earlier. Hello, go on, please.
Okay, please. I just want to add something to that, sir.
Okay, please go on.
Okay. If you want to check the peaks on hour for locations, maybe anywhere in the world, you can also access data center for this NASA. Just try to put the location, then you get the peaks on hour, you download it, and that can serve as a reference too. So maybe I'll send the link. I'll send the link to the WhatsApp group.
Yeah. So thank you very much. Like I said,
thank you.
Like I said, these data.
Thank you very much.
You can get them in bit. You can get them from. There are different sources you can get this data from. But if you're looking for a finished information, you might need to do the calculation yourself, which is the reason why we are doing all of this calculation and explaining all of these variables, so you understand what they mean and the variables and the data you need to do the calculations. So thank you very much. I don't know if there's any other question on these calculations that we have done so far before I move to the Excel.
Let's go forward, please.
Okay.
Forward.
Please, let's move on. We have less than 30 minutes to run this up. Just a moment. Let me open up the Excel and then pull it up.
I can't hear anything.
Okay, I said just give me a moment. I'm working on the exam. Just pull it up now. It should come up in a few seconds.
Okay, class, as he's waiting for him, I would like one of the participants that explain how to test for power factor. Please give us a better light on it. I'm pleading, class.
One of the participants that does what?
Give us a highlight on determining the power factor of a battery or
clamp-on meters. Clamp-on meters that have that configuration inside the meter. You just switch to that and then clamp on. It will give you the power factor reading. Do you get what I'm saying?
Okay, yes.
There are clamp-on meters. Once you put it on the line wire, and then you switch the meter to power factor reading, it will read it for you.
Okay, thank you.
Or maybe it's you use the probes, the positive and negative probes.
Can you see this screen? Can you see myself?
Yes, sir.
Okay, good.
You have to expand it. You have to expand it. There's Greek.
Is it moving?
It's Greek.
Okay,
So,
okay. Yeah. I know. I understand. I know.
Just
this is what you mean, right?
Yeah. Okay. Or you can increase the size, and then you can freeze. You can freeze the top.
I can actually reduce it. What? Just.
No, to be too tiny. No. What you can do is increase the size, then you can scroll. You can freeze some panes.
It has covered the whole, we are seeing the whole page.
You can
freeze. You can freeze.
You can see it, right? Only that
you can see the whole page. You can see the whole page. We can see the whole page.
Yeah, but the things are Greeked.
Yeah, I'm trying to expand them so that I can see them. However, I will explain what the contents are. I mean, it's not. Yeah.
It's a very good one. Oh.
It has made the work very easy. You just put in your values and.
Exactly. So but like I said earlier, it's good you understand the manual calculation, right? This Excel I will be shared to every one of us, but I want to plead because I know some of us got the link to this training, maybe through a colleague or friend, and you may have not made your payment. Please, I want to crave your indulgence to please do your payment, because Engineer Uche will be sharing this Excel to only those who have completed their payment. Please, he had mentioned to me there are 1 or 2 people who are yet to make payment or complete payments.
That's fair enough.
Yeah. So this is the purpose of this Excel is just to make the whole design work easy. And like I said, remember when we started, we talked about the energy audit. You need to know the load that you need to power. So this is an example of that. So you need to put the load here. Now, all these parts, let me put them in blue. Now you need to put the load that needs to be powered. You need to put their wattages. You need to put their quantity. So once you do that, this one automatically calculates, then converts it in kilowatts. Okay, now another thing you need to know is that what time would they be using the load? What time would they be using the load? So this is television. So this is between 1 a.m. and 12 noon, or 12 noon, right? Then this is 1 p.m. midnight up till 12 p.m. in the midnight as well, okay? So what time would they be using this television? If they're going to be using this television in the maybe in the morning hours of 8 a.m., just come to this place and then put this value. No, this 0.15, this value here, put it here. Just add 1.5, yeah. So if you add the 1.5 here, the reason why I need to add this 1.5, okay. I need to create a load profile.
Is this 0.5, 0.15?
150.
Sorry, 0.15. Sorry. Yeah. So just put 0.15. But I just want this. I just want to use it to illustrate. So that if you notice, Okay, sorry, not 0.5. What you're going to put is 150 because you're doing 50 times 3. Put 150 there, right? Put 150.
I suggest you put the total load to be
in watts now. Is the same
so that
thing.
it's
It's in
consistent.
watts.
Instead of one total load, instead of kilowatts, make it watts.
Yeah. Okay. So the point is I can make this in kilowatts, I can make it in watts. But the point is, the point I am trying to make here, like I designed this to make the work easier, right? And I don't want to make it more complex. I could make it so that you could just put an X and it will automatically pick the value, right? But I don't want to make it too complex so that anybody can use it, right? And that's why I left some of these things that you can input by yourself so that you also get used to, some of the intricacies of these things, right? Now, the reason why I'm putting all of this time, the reason why it is important is that I want to create a load profile. With all of this, I can create a very professional load profile with this information I'm having here. Don't worry, you'll be amazed the report that we're going to generate from this information. I will show you the report. It's included in this Excel. I will show you the report. You'll be amazed at the report that we're going to generate. So now it's either you put 0.15 or you put 150. Okay, but for the purpose of this, I have put 150, and 150 is in watts. Okay, so now it is assumed that from 4 p.m. and the reason why I put 4, maybe in the afternoon when the children come back from school, from 4 p.m. they start watching the television, and they watch television up until 10 p.m. they will turn it off. So from 4 p.m. to 10 p.m. you have 7 hours. You do the same thing for washing machine. What time do they use the washing machine? Maybe in the afternoon when the students have gone to school. Maybe someone in the house will now run the washing machine for 2 hours. You need the system to run for the washing machine for 2 hours. You now put the hours, the time you're going to run them from 12 to 1. That is 2 hours. You now do the same thing for all of the equipment. Once you've done the same thing for all of the equipment, what you need to now do is to select your system voltage. If you're designing, what voltage do you want your system to be? Do you want it to be 12 volts? Do you want it to be 24 volts? Or you want it to be 48 volts? Okay, so now this system volt is the voltage of your inverter, like we already mentioned before. So select the voltage that you want your system to be, the voltage of the inverter. So if, assuming we choose 24 volts for the inverter, then let us come back here and select the battery technology that we want. Are we using lithium ion or we're using lead acid? Okay, if you're using lithium ion, the characteristics is different from lead acid. So select the kind of battery technology you want to use. So if we select lithium ion for this very Excel sheet, that's all we need to do. If we have done all of this that I just explained, we can now come to the next sheet. This is the next sheet where the report it will be generated. So if we come here, what you find is that in this sheet, you're not entering anything. The only place you need to enter something is here. The first sheet here. Once you've done all of this that I told you here, you come to this, you see a report. Now, this is your load profile. Your load profile would have been generated automatically. So based on this, you can see your peak, when the peak is happening. And your peak is happening at this point. And at this point, it's about 2,600 watts, or 2.6, right? So this is your load profile. Now, this is the breakdown of your energy consumption. Okay, so you know that your hot plate, remember in our load equipment, we have hot plates. So we have hot plates cooktop, and it uses 2,000 watts. And you use it for, even though it does not ideal, it does not make sense for anybody to put hot plate on solar system, right? But this is just for an example. And the purpose of me putting the hot plate is also for you to see the impact of using those kind of heavy equipment on solar system. It is not recommended, okay? So the person uses hot plate only 3 hours in the day. So if you can now see that the hot plate consumes 40% of the energy. Only the hot plate for 3 hours, it uses 40% of your energy, okay? If, for example, we come here now and reduce this hot plate now, we change it to, okay, we only use it for 2 hours. Let us delete this. Okay, you use the hot plate 6 hours, not 2 hours. You use it in the morning, use it in the evening. So let us reduce it to 4 hours. So 2 hours in the morning, 2 hours in the evening. So this becomes 2. let us see the effect of this on our load profile.
It should
So
be
you
4
now see
hours. It becomes 4, please.
it becomes 4 hours.
Becomes 4. Yes.
Yes. Oh, sorry, I put 2. Okay, it's 4 hours. Sorry. So it becomes 4 hours. Now look at the effects on our load profile. So it has now increased to 31%. It used to be 40%. Now, because we reduce the hours from 6 to 4, it is now 31%. If we reduce it further, to 2 hours, so you use 1 hour in the morning and 1 hour in the evening. So this becomes 2. If we do that, let us look at the effect. It's now reduces. You can now see that our load profile is also changing. Okay, so in the morning, because of that heat, like that cooker, look at it causes a spike in our load profile in the morning and in the evening. It causes a spike. Okay, now this is the breakdown of the energy consumption. So you know that your hot plate is using 18%, and then your fridge is using 29%. So essentially, this is the breakdown of your energy consumption. Just because of these values that you entered here, okay, you can see how this report is being generated. And it's not just about the load profile and the breakdown of energy consumption. It can also go down and then give you the system design. Okay. So now okay, this is the table of the load breakdown. This is the table of it that generated this chart here. We can also go down. You can go down and see the off-grid solar PV and battery system sizes. So for those information, the inverter capacity that you will need is 6.57 kVA. This is the inverter capacity that you need. Now, this is solar capacity. All those calculations that we did, it has already taken place here automatically. This is solar capacity that you need. You need a solar capacity of 6.89 kilowatt peak. Now, the battery technology that you choose is lithium ion. And for lithium ion, it is assumed that the depth of discharge is 90% by assumption. Now, there is something we call cycle efficiency of the battery. If you charge the battery fully and discharge it, you will not get 100% of the energy that you gave into it. By way of charging and discharging, there are losses. So there is a cycle efficiency of the battery. So we assume that 5% of the energy will be lost. Okay, so the cycle efficiency is assumed to be 95. Okay. Now, the battery storage capacity with daytime load. Now, if you have a solar system and you're consuming the energy during the day, it reduces the number of battery capacity that you need compared to when you're not using it during the day. So during the day, you are not in the house, you're going to work. Okay, but you need those energies that you can consume at night. What that does that your battery capacity, you need to decide it to be significant. So I give you an example. Imagine that during the day when the sun is shining, I'm running my washing machine. What that means that it's collecting power directly from the solar panel, okay, and it's charging, and I'm running my washing machine. So I will need less energy at night. I will not need to run my washing machine at night. So what that means, I will reduce the capacity of the battery storage I will need at night. Okay, and that's what this means. Battery storage with daytime load, if you're using daytime load, it reduces that battery capacity to 19 kilowatt hour. If you're not doing any daytime load, you want to use all your energy at night, then what that means is that you need a battery capacity of 25.8 kilowatt hour. Okay, and now this is the system, this is the nominal voltage that we have selected. Remember, we have selected 24 volts. Now let us go and change this into 12 volts. And let us also change the battery technology and see what happens. So if we change 12 volts here, and we change the battery technology to lead acid, let us see what will happen here. You can now see that depth of discharge has changed to 50%. Assuming you're using 50% DOD, right? Now, the cycle efficiency also has dropped to 85%, and the battery capacities has changed, and the voltage of the system has also changed to 12. Okay, so it happens automatically. I have programmed this already with these assumptions, and that's why I clearly stated the assumptions here. Okay, and then the total charge controller capacity that is required is here, is this. Okay, so let's go back and change it to 24 volts. I really don't like to work with 24 volts. Just a moment, I'm admitting some people in the waiting room. Okay, so let me change this back to 24 volts. You can as well use for 8 volts, but let's use 24 volts and let us use lithium ion. I also really don't like to use lead acid batteries. So if this is what we have, so this is the total charge controller capacity that we will need, 287, that is charge controller capacity. And I have also done some estimates. Now, you can choose to ignore this cost. I just did some estimates of how much this might cost, okay, based on the contemporary, based on the market price, the present market price. Okay, PV systems are priced maybe per dollar per watt, okay? So I think I had about 200,000 per kilowatt, okay, to establish this cost. So this is just an estimate. Please don't take this is just an indicative cost. Don't take this as the real cost. You need to go to the market and find out what the cost is. The most important thing is that you know your system design. You know the capacity of the inverter you need. You know the capacity of the battery you need. You know the capacity of the charge controller you need. Okay, and assuming that the person is also using the power during the day, you know that the battery size will now be reduced. Okay, that is the whole importance and essence of this Excel model. It will be shared to every one of us who has completed their payments by Engineer Uche. Okay, so this makes the whole work easier for designers, and it's also.
I have a question.
Okay, please.
My question is: do we have to use the two? Okay, let's see the total. Where you have the total cost? The total cost, please. Where you have the total cost? You brought it.
Yeah.
Yes. Are we going to use for our calculations? Are we going to use battery storage capacity with daytime load with battery storage capacity without daytime load together to do the calculations of the total cost?
No, you can see that the total cost is separate. The battery with daytime load is separate. The one without daytime load is separate.
Okay.
The total is separate. So
that answers my question. Thank you.
Exactly. So this is with daytime load, and this is without daytime load.
Excuse me. The cost estimate, the estimated cost. There is still the formula you use. You said 200,000 naira per kilowatt hour or what?
I suggest you put it in dollars because naira rate is changing too fast.
Okay. What's the formula? The rate.
So for the solar panels, right? So like I said, the rates, the calculation for the cost. And I said you should not give so much attention to the cost. The reason it's just an indicative. Now, how you do that costing is this. If normally you cost solar panels in dollar per watt, dollar per watt or naira per watt, okay? So if you're doing for 5,000 watts, you can now multiply it by the dollar value to get your total cost of the solar panel.
And we now convert to naira.
You can now convert to naira with the prevailing exchange rate.
Okay.
Yes.
Engineer, sorry if I may comment. I think this Excel sheet can be better if you introduce a column to capture the number of batteries, number of solar panels.
So the number of batteries, the number of solar panels will be depending on what capacity you're buying for every unit. That's why I didn't want to include it here. So if you go to the market, you can choose to buy 300 watt solar panels. You can choose to buy 250, you can choose to buy 400. So it depends on the individual capacity. And you can go to the market and decide to choose a different battery specification. You can choose to buy a battery of 24 volts, 200 or 100 watt, 100 amp hour. You can also go to the market and choose to buy a battery of 6 volts and maybe 1,000 amp hour.
I think what the other person is
since it's like a spreadsheet, you can introduce all those variables.
We can do that on our own. No, it will be too cumbersome here. It will be too cumbersome. We can have another spreadsheet to bring in all the earlier calculations. Then whatever figure you get, you bring it into this.
You can now divide it and then get the number that you want. Right? So like I said, I don't want this to be too cumbersome. I don't want to make it to be too complex, right? And that's why I left it just to say. But for me, I feel the most important thing here is that you have your energy, your demand profile. This is priceless. This is very, very essential. Okay, and you have the breakdown of your energy consumption. With this, you can better advise your client that look, this because the problem is this: when people come to you to do solar system for them, they will come with no knowledge of how this thing work. Some will tell you that they want to power 10 air conditioning systems. They want to power their hot plates. They want to power all of this. Okay. By the time you give them the price, they will just keep it on their decks to gather dust. Or you give them a quotation, they'll keep it on their decks to gather dust. So this will also help you to communicate to the client that this is the information you give to me. This is what it is. However, we can change some of this thing. Must you use hot plates? Must you use air conditioning system for this number of hours? Then you can now begin to tweak the design. As you're tweaking it, you're looking at it, how it's affecting the whole system sizing and capacities, and as well as the cost. You know, the cost in this case may not be the real market cost, but it's indicative of how the cost would change. Okay, so you can use this to also engage your clients and make them understand how this thing works and how their choices affect the cost of the project.
Okay, so are you giving us a copy of this spreadsheet?
Yes, it will be distributed.
Thank you very much.
Hello.
Yes, please.
My question is, if you're giving us a copy of this spreadsheet, when and how can we begin to use it on our own? Do we need to buy it, or is it normal spreadsheet? What do we do? I want to know.
So I took you through how you can use this spreadsheet, which is the purpose of this session that we have now. I told you how to input the data here. I told you exactly all the data you need to input. And once you input all this data, there's not so much data to input. Once you input them, this calculation will be done automatically. The spreadsheet, I've programmed it to do this calculation for you.
Okay, please.
Yeah, this is just it will be shared with you. Now, this is just an option. When Uche comes again next week, he will also introduce it to PV-Syst, which is another software you can. Now, this is on Excel sheet. Uche will introduce to PV. So we want to make sure that you have as much options as possible to do your designs.
Thank you very much.
You're welcome. So any other question? Any other question on this?
Not on this. We want you to recommend to us where we can get some of these materials, PV modules and inverters, charge controllers, the best brands in the market, please.
Okay, if you let me you're looking at my screen, right? Let me Google something.
In Nigeria.
Yeah, there's a document I will share with you. Now, there's a rating that changes with time. I think every year. Now, when you're saying in Nigeria does not manufacture PV models. It is manufactured mostly in China, right? But those of them that are being manufactured in China, they have different ratings. I think every quarter or every year, there's a rating agency that rates them based on the best PV models. So among the top, you have GCO, you have Trainer Solar, you have LG. It's not very common, but LG also does solar panels. You have them in among the top brands. I'm just naming them on top of my head, but there's a chart that I will share with you that have this list. And bear in mind that this chart will change over time, right? The same thing with batteries as well. Okay, some people have done, I'm sure one of our colleagues said that you can do some of these tests in their laboratory at Pan-Atlantic University. So I'm not so sure if that's correct. But, sorry? So the point is that these are the areas that our research institutes should also focus on, how to be able to classify this equipment in terms of their quality and standard. In fact, essentially based on standard. Standard Organization of Nigeria, they have some of this equipment, but I don't know how effective they have been in standardizing this product, so that when you're buying 400 watt solar panel, it is 400. If you're buying certain system or certain technology of battery, it gives you what it is. And not buying a battery and within maybe 500 or 800 number of cycles, it packs up. So some of these things, there are agencies that rate them based on laboratory tests. So they subject them to laboratory tests and they publish their findings to be able to rate some of these products. I will share some of.
sir,
I will share some of them that I can find.
But sir, from your own experience, you have
Okay.
employed and deployed some of this material in some of your projects.
Yes.
We're asking for your personal recommendations, please, on batteries and some of these other materials.
Oh, okay. For like I've mentioned some for the solar panel. I mentioned Jinko. I mentioned Trina Solar. These are the most popular one in the market in Nigeria that are at the top. Then for batteries, I will always recommend. It depends on the cost anyway. So sometimes it depends on what your clients can afford, right? So there are high quality lithium iron phosphate batteries. Now, I will recommend lithium iron phosphate. There are different technologies. There's different chemistry.
Those ones are too costly now.
Exactly. So, like I said, if you can afford it, I would recommend lithium. Now, the point is this: it lasts longer. It has about 6,000 number of cycles compared to every other one. So, some manufacturer will actually give you 10 years guarantee or warranty on those kind of technologies.
What of these cycle batteries?
These cycle batteries are okay, but they cannot last as long as the lithium iron phosphate that I've mentioned. Deep cycle batteries, and when you're talking about deep cycle battery, it all depends on the brand.
On the brand, yes.
Yes. So, like I said, I will share some of this information. I have a list of some of them. I will share it. I will share it along. Yeah, some of this brand, the top brand that you can use, I will share them. Like I said, there's no one size fits all. Sometimes you meet the client, you need to look at their budget. You propose certain technologies for them, and then you weigh which one fits into their budget. Then you can work with them. But however, it is important that you make them understand the advantages and disadvantages of all of these technologies.
Okay, PVC. Do we download version 7.2? What version do we download?
Download the latest version that you can find.
It's 7.2.
Yes.
Okay. Thank you.
Please, 200 ampere lithium ion battery should be how much, please?
This is depend on it depends on the manufacturer. All right. You said 200 amps lithium ion battery of how many?
200 ampere lithium ion.
Of how many volts?
12 volts.
Of 12 volts. The top of my head that I will really recommend is Pylon Tech. I hope I'm not. I might still on recording. I think the recording should stop. Let me see. Okay. I'm not so sure.
You can send it. You can put it on the chart so that you're not.
Like I said. Yeah. Like I said, I'm going to share some of this information, please. I'm going to share.
Yes.
Okay. Yeah, I will share it, please. Yeah.
Just the link. The link is better. That's safer for you.
Yeah. Yes. Yeah. All right. Okay. So thank you very much. I mean,
I've not seen myself on the chat.
Sorry. Okay. Please add me to the WhatsApp group. Most people are requesting to be added to the WhatsApp group. Okay. Okay, please, you'll be added to the WhatsApp group.
Okay.
Yeah. So please, should in case if you have any challenge, if you have further challenge and you're not able to reach Engineer Uche, I don't know if let me just drop my contact here. Should in case you're unable to reach Engineer Uche and you're having challenge, please, you can also reach out to me.
Okay, thank you very much. There are some numbers we have dropped at the chat box to be added to the WhatsApp group. Please, Engineer Uche should look at them and add us to the group. Thanks.
Okay, so that's my number on the chat group. If you go to the chat, you see my number. I mean, sorry, not chat group. That's my number on the chat, on the Zoom chat. If you are unable to reach Engineer Uche for any reason, you can also reach out to
0816.
Yes.
0816-229.
Yes. 6020.
6020.
Yes.
Sorry, if I may ask a question, considering the space that will be required for installation.
So please, for all of you, add me to the WhatsApp group, please. Maybe, except I will need to start copying out these numbers. Send me a message. You have my number. Send me a message on WhatsApp. If you're not able to reach Engineer Osei to add you, send me a message on WhatsApp. I will do the addition myself, please. So I think with this, we have come to the end of.
Please, I was asking a question, please.
Today's session. I really liked it because it was very, very interactive, and I can see the active participation of almost everybody in the class, and I'm happy about that. Please let us keep it up. Next week Saturday, Engineer Osei will come up with the PVCs, and I'm sure it will be more interesting than what we've had today. In the absence of any other question, I want to bring this.
Please, I was asking a question. I don't know if you can hear me.
Okay, please go ahead.
I'm saying to conserve space, isn't it better to go for the higher voltage batteries so that you have less number of batteries? Then how does that relate to cost? Are the 24-volt batteries twice the price of the 12-volt batteries? Thank you.
Okay, just a moment. Let me respond to. So we are talking about going to a higher voltage. The thing about voltage and amperage, that the higher voltage you go, the lower amperage you get. Okay, so if you can, it is normal to see a battery. In fact, you see some people, they use 2-volt battery. The reason they go for 2-volt battery is that if you're using a 2-volt battery, you can get a very high amount of amp hour. Okay, so you now need to combine them in series to arrive at the certain voltage that you want. Some will even choose to go for 6-volt battery. So if you see the battery that is rated for 6 volts, always look out for the amperage. Amperage is usually high. Okay, you could see a battery of 6 volt and a 1020 amp hour, right? So it all depends on the dynamics. And mind you, please note, in our last class, I think I explained this. In terms of electricity, what you're consuming is the current, not the voltage. You're consuming the current, not the voltage. And that's the reason why some people prefer a higher current and a lower voltage. They can always augment the voltage to arrive at their system design voltage. Okay, so there are different situations and different views to this. Hello.
It's clear.
I don't know.
Thank you. I'm clear.
Okay. All right. So, is there any other question? Okay. So, thank you very much all for your active participation.
We'll be expecting the Excel sheet, please.
Yes, you will.
And the lecture for today, so that we can download it.
Okay. Yes, sorry.
Hello. Hello.
Yes.